Okay, today we are going to start another topic for the graph theory. So first, let me just recall what we have learned. 这可以吗? What we have learned from graph theory, right? So usually we assume G is a graph. So which means it has vertex and edges, right? And so G usually we denote this as V over G. V is a vertex and E is a set of edges. And today we are interested in looking at the matching problem. So let me give you an example. Start with an example, right? So suppose I have a few people. Say I have 5 people. They are A, B, C, D, E. And suppose I have 5 jobs. This is little a, little b, little c, little d, and little e. Of course, different people might be qualified for different jobs, right? So assume this is going to be the restriction. So the restriction is that's a qualification. So assume A qualifies for the job CD, B qualifies for the job C, and let me write here. C qualifies for the job AE, and D qualifies for the job CD, and E qualifies the job B little e. So this is the qualifications. So now the question is can we find that there exists a feasible matching of all of these 5 people to these 5 jobs. Okay, so that's a question, that's a problem what we are considering. Of course, in reality, you can consider more complicated problems, right? But here we just consider an easy one. So I have 5 people, A, B, C, D, E, and I have 5 jobs, little a, little b, little c, little d, little e. And I do have a kind of restrictions, which is qualification, right? So I say A qualifies CD, B qualifies C, and D qualifies AE. People D qualifies CD, and E qualifies B little e. Right? So now, as a manager, maybe I have to make a decision whether I can assign every job is going to have 1 people which will be qualified for the job. Right? So now, of course, for the graph theory, what we want to do is build up a graph and then study the property of the graphs. So the graph what we consider is, so G is a graph. What I'm going to consider is I have 5 people. So I'm going to denote this is A, this is B, this is C, this is D, this is E. Right? And I have 5 jobs. So I'm going to little a, little b, little c, little d, little e. And the qualification is realized as an edge, right? So for example, A qualifies CD. So A qualifies CD, C and D. And B qualifies C, so B qualifies C. And C qualifies AE, so C qualifies A and E. And D qualifies CD, so D qualifies C and D. E qualifies BE, so E qualifies B and E. Okay, so now the goal of the now that's a place why we mention the name of a matching, right? So my goal is I want to find a family of edges. I want to find a family of edges such that each person will be assigned for one job, right? So my goal is I want to find a family of edges such that I'm going to find, because each people can only be assigned one job, right? So therefore I want to find a family of edges such that I don't want two people assigned to one job or two jobs assigned to one people, right? So in that case is I'm going to make assumptions that any two edge have no common endpoints, right? Common vertices. Okay, so that's exactly the restriction I'm going to put, right? So an edge should not have two common vertices, right? So two people will not be assigned to one job, or one people will not be assigned to with two jobs, right? So is it possible to find such an assignment? So that's what the idea of the matching kicks in, right? So generally, what is a matching? So because my assignment basically says no two people will be assigned one job, and also there are one people will not be assigned with two jobs, right? So that's realized as no two edge will share a common vertex, right? So therefore that's give us one definition. So in the graph theory, assume G is a graph, and suppose I have a family of edges, right? So a set of edges is called independent. If no two edge will share one common vertices, right? So in the language of a graph, so that's exactly corresponding to no two edge are adjacent. So that's the name of the independent. Independent means there will be no two edge. They are adjacent. They are going to share the they are going to share the common vertices, right? So in other words, is I try to find an independent set from this graph such that everyone has one job, right? So therefore every vertex has to be contained in this independent set, right? So we can have another concept. So say let M be a set of vertex edges. We say a vertex, say V is covered by M. So if V is incident to an edge in M. Okay, so let M, if it's a set of edges, right? A vertex is covered by M, so which means V is incident, so which means that's an endpoint. That's an endpoint to an edge in M. So in the language of this covering, right? So basically what I mean is I want to find an independent set from this graph. I want to find an independent set from this graph such that all of the vertices will be covered. And can we do that? The answer is to this graph, no, we cannot do that. In this case, the answer is no. The reason is if I look at the vertices A, B, and D, and these are three people. And then if I look at the jobs, little c and little d, right? So you notice A, B, C will only be qualified for 2 jobs. Will only be qualified for 2 jobs. And if I'm going to assign A to C, say then B will not be able to assign it to C, right? But that will leave B with no job, right? So there's only way to do assignment is you have to assign A to C, right? B to C, right? And then you can only assign 1 people to D, right? And either A or D. So that will leave A or the other one have no job, right? So therefore, there's no way to find such a matching, right? So, but anyway, this gives us quite good motivations to consider what we call independent and independent set, right? Independent set, and if it's an independent set, and then we can also actually this covering vertices is covered, right? So basically, another concept is vertices is going to be covered. Okay. Sometimes independent set is also called a matching, right? Because for independent set, let me give you another example. Say I have so this is a graph G. And I have, say, this is a little A, B, C, D, E, F, G. They are edges, right? And these are vertices. Then I want to say, so for example, if I look at a set B and D, if I look at these two edges, I claim this is independent. Because these 2 edges shares no common vertices, right? Common vertices. So that's this is what we call independent. Let me give you another example. Say for example, I just pick one, pick say a B, G, and F. This is independent. If I look at this 3 edge, right? This 3 edge, B, G, F. Right? So apparently these 3 edge they are independent. So they don't share any common vertices, right? So that's what we call independent. But as long as you have one independent set, for example, this is a V1, V2, so this is V3, V4, V5, V6. These are the vertices, right? And suppose I give you one independent set because B joins V1, V2, right? So I say V1 is matched to V2. D joins V3, V6. So V3 is matched to V6. Right? So that's a matching. So because the 2 endpoints of one edge, I say that's a matching. Right? So for example, this independent set, this gives me B, V1 matched to V2, G, V5 matched to V6, right? And F gives a match V3 goes to V4. Right? So that's again that's a matching, right? So that's the name of the matching kicks in, because for an independent set, you see all of these vertices are different, right? So that's what we call the independent, because you do have different vertices for this set, right? And this also gives me a match V1 to V2, V3 to V6, and here gives a match V1 to V2, V5 to V6, and V3 to V4, right? So that's what we call matching. Yes.
稍微停一下。